Hello and welcome back to my journey building Nova CVS. In the last video, we saw how you can use Processforge to completely abstract the backend of running an OpenMC simulation. In the last video, we deployed a Docker container on Railway, fired off the MSRE experiment, watched it run and succeed without ever installing OpenMC in my local machine, so everything ran in the cloud. But running the code is only half the battle. In the context of regulatory submissions, licensing, and other regulatory activities, the outputs and processing them is where the value is. So in this video, we're going to dig deeper into the outputs. What we are trying to do is to demonstrate how Processforge manages a change in the input with a change in the output. And we'll also see how Processforge transforms complex OpenMC outputs into cloud-compatible ZARR arrays that you can then load in Python and visualize easily. So this is the goal of this video. If you like these kind of videos, please subscribe and share it with your colleagues who might be interested. We are building modern tooling to run modern code to support regulatory submission and licensing activities in the case of nuclear power plants, but these tools can be used in other domains as well. Let's begin. So let us quickly review our flow sheets that we showed the last time. So I'm going to open up my flow sheet and we'll just do the quick review. Here you see I have on line 10 my provider as OpenMC, and the URL is this Railway URL, which basically tells you where to run and offload this this computation. I have materials, exactly what you would expect in OpenMC materials. You can look at the OpenMSRE experiment and sort of it's exactly the same thing as that. Here is a more interesting one. On line 76, we have the OpenMC solver, which is a solver unit, and we have basically a solver config. This is how Processforge knows exactly where to pick up the values from. Here we have 20 batches and 20,000 particles, and then a geometry config. So this is our flow sheet. I'm going to run this. So I type in pf init. This is my flow sheet. As expected, Processforge creates a directory. For example, there is a log file and so on. It also knows that this is let's say a remote run where it checks the URL. It will not create a Docker compose for it because this exists remotely. Then I say pf plan, flow sheets, OpenMC, MSRE. So let's go through the output of that. Basically, it validated the flow sheets and then essentially made a ping to the service deployed. It also created a mermaid diagram. If you're familiar with this, it will sort of map out that as well. And then I say pf run flow sheets, OpenMC, and MSRE eigenvalue. So basically, when you are using a dynamic or a simulation which uses Docker containers, you use ps1. For steady state simulations, you can use pf apply. But in this case, we are going to do the pf run. What has happened, as we saw the last time, Processforge processed the flow sheet, looked up the variables, registered the units, and then offloaded it to the container client. It does all of this via what is known as the OpenMC provider within Processforge. We can talk about the provider and how it's set up, but basically it reads the flow sheets and then offloads it to the container provider client. It might take some time to run, depending on how complicated your simulation is, but the idea is that this is now running on railway.com or any other cloud provider of your choice. You can take a look at, for example, the railway logs and so on that we saw the last time. So we're just going to wait for it to complete. So that didn't take long. That executed successfully. Let's just see what it did. Basically, it ran the flow sheet, and then this is the interesting piece. It wrote an output in the outputs directory in msre eigenvalue.pfarchive. So it ran a simulation in the cloud and then wrote something in the output directory, and then it provides us with some additional details about what else happened. So what we're going to do is to show you what actually Processforge does. So let's explore the output directory and see what's in there. So let's look into this outputs directory. Here you see the msre eigenvalue.pfarchive directory. Before we look into the data, let's talk about this directory. If you recall, I had told you that physics is not the only bottleneck when it comes to new nuclear energy deployment. There is regulatory oversight, there is quality assurance, there is documentation, and other activities related to licensing that cause massive hurdles. Traditional simulation workflows can be messy. 6 months from now, a year from now, how would you know what version of the code that you ran that produced this exact output? This is where Processforge solves that problem via this pfarchive directory. Think of it as a Terraform state file. So if you're familiar with Terraform, it is similar to that. It is an immutable receipt of what happened. It contains hashes of your files. So when you hand it to the regulator, they will know exactly what caused this input and output. So let's dig deep into what exactly is in this msre eigenvalue pfarchive. So let's take a look at this directory. Here you see, for example, artifacts.json, index.json, the latest and the latest run details, results, which is what we're going to look at, the runs and the snapshots. So essentially you have an archive of all the things that happen for that flow sheet. If you look at, for example, the runs directory, you will find a run JSON. So if I just say, look into this JSON, you will see what exactly the solver that was used, the kind of units and what was gathered, for example, the tallies and so on when it comes to OpenMC. And then this kind of a provenance information and the versions used and so on. That's interesting. That's in the runs directory. So let's go back up a directory. And then I see here in the results directory, I see, for example, the result of the run that we had. So I say, go into that directory. And here you have the ZARR schema and the results.zarr. So let's take a look at what's in this results.zarr. Now, ZARR is a cloud optimized format for arrays. And so this is why we use the schema. So you can put this in S3 or other tools that can then efficiently, let's say, query and be plotted and visualized. So what we're going to do now is look at what's in the results.zarr file. So I've created a small Jupyter Notebook to just show you how easily and quickly you can process ZARR files. But you can use any other tools. As I said, Processforge also has this facility to update the H5 files into S3. But ZARR is a much better format for cloud-based systems. And so we're going to use that. In this case, I'm using a library called xarray, which is a Python library. I'm using ZARR. And I have basically my some sort of initialization here. Now I am loading my ZARR store. So in this case, my path is here. And then I have my solver, and I can run this. As you can see here, the effective K is around 1.0547. So this is from the results.zarr file that we had. And essentially, you can then compute the K effective like I'm doing here. It is exactly what you would expect, which is basically looking at the ZARR data that is provided by the simulation. And then you have the K effective, and then you have, for example, a plot of the flux distribution. So now this, at the moment, OpenMC DAG-MC geometries are not there. We are just assuming a computational, let's say, geometry. But the idea is that you can then take, for example, the flux mean from the tally and then plot it over here. So in this, let's say, very simple steps, I've been able to look up the results and then plot them in Python. But ZARR is let's say, a flexible format. You can use this in many other languages and libraries. But what we just did was took a look at the output of one run of ProcessForge and then processed it and showed you how you can plot it. Let's make some changes and things will get a little bit more interesting. Now, let me show you why this run and state management is so powerful. What we're going to do now is go into our flow sheet and change the particle size or the batches, and then see how ProcessForge manages it. Okay, so let's enter our flow sheet. In this case, what I'm going to do is just go down, and here, instead of 20 batches, I'm going to have, let's say, 15. Okay, just for the sake of our demonstration, I'm going to write that, and then I'm going to quit it. Okay, so now then I ran my plan and init workflow again. So basically, let me just clear this. PF plan, flow sheets, OpenMC, eigenvalue. So now it should detect, for example, that the batches has been updated from 20, it has been reduced to 50. It already knows that there is some existing, for example, data available via the snapshots that we have. And now I'm going to run the flow sheet. So it is PF run with 15 batches. Again, it has been sent into the Docker container to run it. And we're going to, once it's complete, which it should take, a little bit shorter time because we have reduced the batches as well, it would provide the same data back, and we'll just compare the outputs between different runs. So let's just wait for it while it's completing. Okay, so now it has completed. It didn't take that long. So if I'm just going to say a new command, pf runs, plural, flowsheet, OpenMC, eigenvalue. What this is doing is showing you the two, let's say, run IDs here, these two, and then the timestamp, and then sort of what was the output present at disk, and so on. So this way you can check, for example, if a particular run was indeed present and the outputs are present on disk. So let's just analyze the outputs folder now, as we did with the previous one. So we are in the eigenvalue pfarchive folder. So if I just go here you will see, for example, in the runs folder, we have two runs, which is basically at different times, and it has a hash of let's say the flow sheet. So you can be sure that this was done in a particular, let's say, version of the flow sheet. In the same way, if you look at results, you will have two different results. So in this case, I'm going to EFBE, that's the second one. I'm going to go into that. Exactly what you would expect, the results.zarr and results.zarr schema, which we will then use to plot in our Jupyter Notebook as well. So this is how you can see that the same flow sheet has two different versions and two different runs. So let's look at the Jupyter Notebook to explore what changed. So I'm back in my Jupyter Notebook. In this case, I'm just going to update my output to this newer output. So then essentially everything else remains the same. I can see here the K effective and the sort of the standard deviation changed because I reduced my run. I hope you saw that. If you haven't, just press pause and you can see it. And then I can see, for example, the tallies, more or less the same. But the point is that you can now load a different ZARR file, and you can imagine doing a comparative analysis between these files. So what did we achieve today? We ran OpenMC simulations in the cloud. We proved the regulatory traceability through pfarchive, and that whole runs and snapshots and so on. We extracted the physical data from the results directory into a Python environment using xarray and all these other tools. We also showed you how you can upload all of this, the actual OpenMC outputs, into S3. And by separating execution and analysis, We focus on the engineering and let ProcessForge handle the execution of these runs. This is the real power of ProcessForge. In the next video, we're going to show you an even deeper topic, which we're going to couple codes together. And we're getting into how ProcessForge manages multiphysics, for example, in a single flowsheet. Thank you so much for joining. If this is of interest, please feel free to reach out. Please subscribe. I would love to work with you exploring this topic a little bit more. If you have flow sheets or projects that you think that might be interesting to try with ProcessForge, I'll be very happy to engage and build a flow sheet for you. And then we can see how this can be improved. Thank you so much. I'll see you in the next one. Bye.